All right, so how exactly do you find grand formula mass? Let's just say we had, let's just use CO2 for example. So what we want to do is identify the element on the periodic table and then find the atomic mass and add those together. So let's take, for example, carbon. Carbon is 12.011. We want to round to the nearest tenth for these calculations. So this is just going to round to 12. And oxygen on the periodic table is going to be 16. And we have two of those by the subscript here. So 16 times 2, 32. And these are AMU, by the way. Let's just make sure we have our labels. 32 plus 12 is 44 AMU. So that's the grand formula mass for CO2. Let's move on to a more complicated example. Here, let's use, I guess, barium. And in parentheses, let's have OH subscript 2. So in this case, let's just do the same thing. Let's find barium. That on the periodic table is going to round to 137.2 AMU. And then in parentheses here, we're just going to add the OH2, which we need to find. In this case, the OH is going to be equated to oxygen, which is 16 AMU, and hydrogen, which just rounds to 1. And the subscript here, when you have a parentheses and a random coefficient here, it basically means that you want to calculate whatever's in the parentheses and then multiply that by the x value. So in our case, the x value is going to be 2. And so we have, let me scroll down here, we'd have 17 times 2. And that's going to give us 34 AMU. So we just take this and this, and we add them together. We're going to get a grand total of 171.3 AMU. All right, let's move on to our final example for grand formula mass. We're going to have CH4, this little symbol here, 5H2O. Alrighty, so let's just go left to right. So we have carbon, which is going to round to 12. We're going to have hydrogen, 4 hydrogens, so 4 times 1 is 4. I'm missing the labels, but it's fine. Now, what is this symbol here? I've explained this before. This essentially means it's a system. And what you want to do here is add, right? A lot of students think you need to multiply here, but you want to add. So you're basically adding on whatever you have here. In this case, it's very interesting as well. Think about this as having parentheses, right? You want to do this calculation first and then have the coefficient applied to the H2O. So let's find H2O first. H2O, so 2 hydrogens will just be 2. And then the oxygen will be 16. That's going to be 18 AMU. 5 times 18, because we have the 5 coefficient here, which had to be applied to the H2O. That's going to give us, let's see here. Actually, let's bring this all over here. Oops. Yeah, let's bring all this over here. 5 times 18. All right, so that's going to give us 106 AMU. Alrighty, so that is going to be the grand formula mass for this compound right here. Alright, so let's talk about the relationship between moles and volume, and let's also mix in grams. So exactly what you need to know is that the most important thing here is at standard temperature and pressure, you want to know that 1 mole is equivalent to 22.4 liters of particles. So 1 mole can literally be any sort of element or compound, right? But let's dive into some problems and really just figure this out. So let's say we had 10 grams of NH3, and this was obviously at standard temperature and pressure. I'm going to drag this down a little bit. All right, so how would you go about solving this? Well, the first thing you want to recognize is that you are starting with the grams, and you want to get this into liters, right? So I should probably write this into liters, question mark. All right, so how you go about solving this is by setting up a equivalent fraction. So let's just put 10 grams at the top, 1 at the bottom, just to represent it as a coefficient. And then you're going to bring this over and you want to cancel out the grams, right? You want to convert the grams into moles. And so how you do that is the fraction at the bottom here is going to have a grams because these two are going to cancel out. And we know we want to convert this to moles, so 1 mole is equivalent to what? Well, in our case, we're going to have NH3, right? So NH, let me just bring this over. So we're going to have NH3, which is going to be nitrogen, which is 14, and then 3 hydrogens. So that's going to give us a gram formula mass of 17. Let's go back over here. So we're going to have 17 grams for 1 mole. All right, perfect. So now we have the mole amount. So from here to here, we went from grams to moles, right? But we still have to have this missing section here where we go from moles to the liters. So how you do that is we already know this relationship up here where 1 mole is equivalent to 22.4 liters. So if we set this up, we want to cancel moles, and so moles will go on the bottom. So 1 mole, and that's going to be equivalent to 22.4 liters. Now we can just multiply everything across and divide by everything on the bottom, and that'll give us 13.18 liters. That's our answer for that. All right, let's move on to a second problem for this example. And let's say we start with volume. We want to get grams at the end, so we're going to have to convert to moles and then finally grams. So how would we go about doing this? Well, it's very similar. So let's say we had 70 liters of O2 at standard temperature and pressure, and we want to get this to grams. So in the process, you're going to be converting this to moles either way. So we're going to set up our equivalent fraction, 70 liters over 1, and that's going to be equivalent to liters on the bottom because we want to get rid of the liters, right? So liters here. So we know we want to convert this to moles, volume to the moles to the grams. So 1 mole and then 22.4 liters on the bottom. And then in the other parentheses, because here we went from volume to moles, and now from here we want to go from moles to grams. And so moles on the bottom, we want to cancel the moles, so we're left with the grams. And so we know 1 mole, and then we have O2 here. O2's gram formula mass is just 16 times 2, so that's just going to be 32. Multiply everything across, divide by everything on the bottom, and you're going to get 100 grams as your final answer. All right, so to understand the relationships between moles to particles and vice versa, you need to know Avogadro's number. And so moles in general are just a unit of measure in chemistry, right? It's used to measure quantity. And so what he defines it as is 1 mole is equivalent to 6.02 times 10 to the power 23rd molecules. So let's say we had a problem here, right? Let's just dive right into a problem and see how we can use his number here to help us solve. We have, let's not do 10 grams. Let's just say we had 0.75 moles, right? We want to convert this directly into the number of particles. So how would we go about doing that? Well, we know there's a direct relationship. 1 mole is equivalent to 6.02 times 10 to the 23rd particles, right? So we can set up an equivalent fraction just like we've done before. And so we have 0.75 moles, which is our given supposedly. We put that over 1 in an equivalent fraction. And let's set this equal to number of particles. So we're going to have moles on the bottom because we want to get rid of moles and end up with particles. So the moles will cancel out. And we know that 1 mole, like we said before, is going to be this value up here. 6.02 times 10 to the 23rd particles. And if we multiply across, that's going to give us a grand total of 4.515 times 10 to the 23rd particles. Right, we're just using that relationship to find the number of particles. So let's go down here. Let's do another example, particles to moles. Let's say we had 12.01 times 10 to the 23rd particles or molecules. And this is over 1. And so we have our equivalent fraction here, right? And so we want molecules at the bottom and the moles on the top. And we know 1 mole, should have written moles, but 1 mole is equivalent to 6.02 times 10 to the 23rd. That's a really important number. Make sure you remember that for your tests and stuff. So if you just put this into your calculator, you're going to get 2 moles. And that is our answer. All right, so what is the empirical formula? Well, a simple definition for it would be that you're essentially getting the lowest whole number ratio between the atoms of elements in a compound, right? So this will make sense when we do a practice problem, but essentially when you are given, say, grams, or in our case percentages, which you can convert to grams, you're going to find the number of moles, and then from there you're going to find the ratio between the moles, their closest whole number ratio, and from there you can find the empirical formula which encompasses that very characteristic. So let's scroll down here and you'll find that everything is in percentages right now, right? 40% nickel, 16.4% carbon, 43.6% oxygen, and we need to convert this to the empirical formula. So first thing you need to realize here is that all the percentages add to 100%. And so there's a direct relationship here between the grams and the percentages. And so we can just assume that for nickel, there's going to be 40 grams. Put that over 1. For carbon, it's going to be 16.4 grams of that in this compound over 1. 43.6 grams for oxygen over 1. And like always, if we're trying to find the moles, we're just going to set up our equivalent fractions. The moles will be in the top, right? Because that's what we're trying to get. And now we just need to find the atomic mass of each of the elements. For nickel, it's going to be rounded to 58.7. Carbon rounded to 12. Oxygen is 16. And this is going to give us that value for moles. This is going to give us this. And this will give us that. Right, so from here you want to identify the lowest value here, right? Because you're trying to find a ratio. And so in order to get that ratio and get whole numbers, you want to find the lowest number in which you can divide everything else to get that ratio. So in our case, this is going to be the lowest, right? This is a little victim here. So we're going to bring everything down and divide. 0.6 divided by itself. That's just going to give us 1, right? That's one part of our ratio right now. And let's just do everything else. 1.3667. Remember, these are moles, and we're just dividing them by the ratios of each other. That's going to give us, not exactly 2, but that's going to give us approximately 2. And it doesn't have to be exact, but it needs to be close enough so that the values do match up. And you have 2.725 divided by that. And that's going to give us approximately 4. 4. All right, so you'll find that you're going to have this little ratio here, 1 to 2 to 4. And each of these link with one of the elements, right? This one right here is linked to the nickel. This one right here to the carbon, and this one right here to the oxygen. So now we can write them correctly. So we're going to have 1 nickel, and then for carbon we're going to have 2 because that's the ratio. And then for oxygen we're going to have 4. And that there is your empirical formula. You'll find that that is the simplest simplification for this problem because you can't divide this any further, right? Let's say you had carbon 2. Sure, you can divide it by 2, right? You'll get 1 carbon, and you can divide oxygen 4 by 2 as well to get O2. Except the nickel now, you can't divide it. You can't have nickel 0.5. That just doesn't exist. Or at least doesn't exist when you're trying to get it in simplest terms for the empirical formula. Alright, so let's talk about the molecular formula. So the molecular formula is sort of tied into the empirical formula. Now the definition of it is that it's going to show you the actual number and also the kinds of atoms in a single molecule. So how I like to think about this is that the molecular formula is simply the empirical formula scaled, right? Now it's not going to be in the same units because you're not writing it really in the same form, except you're going to be using a certain scale factor to write it in a different form that's going to be related, and that's why it's referred to as a molecular formula, because you're writing it still in molecular form. So the 2 steps that you want to take is, first you want to find the gram formula mass for your given, right? So gram formula mass. And then you're going to want to find the scale. You want to find the scale, and how you're going to do this is you're going to use or find the molecular mass or gram formula mass in this situation. So this is whatever you found up here, and you're going to divide that by the empirical mass. So in order to do this, say you're given something like 16 grams of carbon, 5 grams of hydrogen, or something like that, you're going to have to use the empirical formula first to find the empirical mass, and then find the molecular mass. So your molecular mass, this value right here, is before the empirical. All right. So let's just have a practice example real quick here. Let's say we had the empirical formula of C2H4 oxygen. So how you want to do this is find the empirical mass, because that's the first section here that we need to find. So C2 is going to be equivalent to 24. We're going to add H4, which is just going to be 4, and then oxygen is 16. So that's going to give us 44 EMU. Right? So now we know our bottom part. But we still need to find the molecular mass. And so how do you find the molecular mass? Well, in this case, you're going to be given something called the molecular mass, right? You're going to be given the molecular mass because you're not going to be explicitly solving for it. So your molecular mass, let's say for this situation, it's something, say like 88, right? It's going to be 88 grams per mole. And so what you're going to do with this equation is this equation helps you find the scale, right? And so then using this scale, you're going to find the molecular formula. So since we know the molecular mass is going to be 88, and then we have the empirical mass, which is 44, we know the scale is 2. And so the scale from the empirical formula to the molecular formula will be 2 times. And so what do we have up here, right? What do we have up here? Let's just bring everything down. So we're going to have C2H4O as our empirical formula, except now that we have our molecular formula, everything is going to be applied to a 2x scale factor, right? So 2 times 2 is going to be C4, 2 times 4 is going to be H8, and 2 times 1, it will just be oxygen 2. And so that is your molecular formula.